Hi friends, so we are here to discuss risk conscious operations management of complex engineering systems, and this is second week, and the topic is dependability engineering. If we talk about the availability, there are two very important factors in the plant. They are capacity factor and availability factor. Any plant is judged by what is its availability factor. Okay, and these two together, let's say if I say my plant's availability factor is 97% and capacity factor is 100%. It doesn't require any explanation that these plants are operating very well. And if I have to talk about some complex engineering system, they operate for more than an year also sometime. Normally calendar time is taken, the mission like 8760 hours in a year, or you can say 12 months, or 52 months is the period that we have, and for what fraction of time the plant remains shut down. So there are some systems they may not require shutdown during the year. Why? Because they are designed like this. Simple. Let us take Indian pressurized water reactor. The fueling is done online. That means, unlike pressurized water reactor and other reactors or boiling water reactor, which need shutdown for fueling. That means removing the irradiated fuel and charging with the fresh fuel. So for PHWR don't require any shutdown. So it is not surprise that these type of reactors, I am very proud to tell as a ex DI person that our reactors, they have made world record of operating for more than 2 years continuously. So why I have brought out this issue? It is availability was 100% for 2 consecutive years. There was, I think, some figure of 200 plus, almost like 24 months and more actually. Okay, and other one is reliability. Suppose if the plant trips for even once, then the plant reliability is impacted. Maybe we can start in a very short time, but it is affecting the reliability. But availability is affected in a very limited way because the shutdown time was very small. So shutdown time is the factor that determines the availability. If it is not shut down, it is 100% in a year. Okay. Now reliability we have discussed, and availability also connects with the maintenance. As I mentioned, the fueling requires one thing, and then shutdown activities or maintenance activities, they also require shutdown of the plant. So that means then it is a question of increasing the maintainability. So we will be discussing availability and maintainability part here and part in the next lecture, because they are very important when we look at the plant from capacity factor or availability factor point of view, and that also tell directly or indirectly how is our maintainability, because it reflects in unavailability. Okay, so simple definition of availability is that probability that a particular component or system will be available on demand. It has got, if the system is available, if it is giving us electricity, 100% means for the whole year it has given us the electricity, it was available. Availability has got another, so this is one of the uptime and downtime concept of availability that we discuss more. The second concept of availability is basically applicable for standby systems. So plant has got operating system and standby system. Standby system availability means they remain, as we mentioned, it remains dormant or passive, or they are, when the demand goes, those systems or those actuation signal goes, those systems have to start. Let us say diesel generator set, okay, it remains passive, in standby mode. Now when the demand goes, then only it has to start. So diesel generator has not started. That means there was some failure which was not detected and it remained passive during shutdown. So the demand failure probability itself forms the component of unavailability, and this unavailability is intuitively built into the probabilistic risk assessment model of the plant. So if we compare this with the RAMS approach, along with the risk and then the initiating event, they give us the reliability quotient of the plant, because initiating event or the transient, they only trip the systems. So what we are coming to is all these factors together, they can be easily captured in a risk model of the plant. So if I see the conventional definition of availability, it is called, and let us name it operational availability. Okay, this is nothing but uptime. That means in a year or in a given period, how long the system was up and how long it was down. So that means uptime divided by total time. Total time is made up of uptime plus downtime. That will give us its very simple definition of availability. Okay, and this is also called steady state availability. Actually, the uptime accounts for operating time, as we discussed, and normally the shutdown time is basically goes or apportioned as maintenance time. So or any specific industry like issues, breakdown or preventive maintenance. For example, in nuclear plants, we have one additional element, fueling. So some plant, like I mentioned, pressurized heavy water reactor, they need not be shut down for fueling. Fueling goes online. So this goes off compared to their counterparts like PWR, BWR, where they need shutdown. So that time goes. That means the plant design has inherent provision to enhance the availability of the plant. Okay, whilst the other component is even though fueling may not require shutdown, but other systems which are operating for extended period of time, they require shutdown. So that second component becomes relevant in such industry, that plant had to be shut down, if not for fueling, at least for maintainability. So these are the factors. So the point is, sometimes industries, they impart in their design or the nature of their operation itself the maintainability aspects, improvement in maintainability or availability aspects. So let us take a simple demonstration or illustration. So as we said, availability as a function of time is equal to all the T term, that is up term. This called plant was up and it was shut down, up and then it was shut down, like this sequence. So these are the so let's say this is for the complete year. That means we got 3 interruption. So 3 interruption means 3 times. So reliability got adversely affected because of interruption. But had this component would have been small, the availability would have been the minimal. So this is the difference between reliability and availability. So up terms, they become the plant uptime, then up term plus down term. So these terms TD, T1D, T2D and T3D, they provide the downtime, or so availability becomes total time divided by uptime divided by the total time. So this is a very simple and elegant and most extensively used for estimating plant availability. And here the one significant thing is, if you want to relate capacity factor with the availability, then this then the capacity factor, this is for the TU1 is the availability for this capacity factor, T2 for this availability factor, capacity factor, and various other things. So that means we want to further analyze at what capacity this plant has operated and that contributed to the availability. So this is another view. Otherwise, it is the capacity factor term is not there. Simply availability uptime and downtime we have, and we give the plant availability. So from one single chart, you have so much of information available for characterizing your plants. Now, one was that approach directly uptime, downtime, and all that. But availability calculation for complex systems or for that complex behavior, or it requires a dynamic approach. And like simple, if I compare fault tree, event tree, fault tree has got either component operating or shutdown. There is no in between stages. Event tree also up and down, a header event, we say system at system level. But sometimes as part of risk analysis or reliability analysis, we have to account for maintainability aspect. Sometimes we have to account for availability aspect. So the Markov models are models. They are also called state space diagram. Okay, we'll see how they look like and all. First, let us understand if reliability block diagram was the primitive and the simplest approach. The Markov models are basically meant to handle the complex scenario where, for example, it need not be fail or success. It could be fail, partially fail, and success, failure. So system is operating successfully, one state. System has gone to degraded state, so the second thing, and system has totally gone to the fail state. Let us say 3 systems are required for a success. One system failure, that means our availability factor or the reliability factor has come down, because there are only 2 systems. One system has failed out of 3. So it is a degraded state or compromised state. And so these kind of things, they require modeling using Markov approach or state approach. Now, so what are the complexity? If there are more than 2 states, or even 2 states also, you can develop a Markov model. We will see that. But it is especially required when we have to see the metrics for different situations for the same configuration. Accounting for effect of repair and maintenance. It is a very effective way if we want to assess impact of changes in maintenance parameter or repair parameter, number of repair stations or maintenance capabilities and all that, human resource required for that, and and then more than 1 repair stations, as I mentioned here. If I have more than 1, how I will account for it? Fault tree and all is not possible, but here we can see their impact, how it is affecting their plant availability. Other plant specific conditions, like I told you, for nuclear plant PHWR, we have the plant shutdown is not required for fueling. Such situation require dynamic modeling. Consideration instrumentation. Now for the demonstration, we are considering 2 out of 3. There are in safety critical system, if we have to monitor one parameter, let us say temperature. Now that temperature sensor may go faulty, or my channel may go faulty, but I want that signal in the control room. So what I will do? I will use redundant techniques. That means for the same sensor monitoring, I will I'll monitor, I have 3 channels for monitoring the temperature. So, if one channel goes out, 2 channels are there, they are monitoring. So, I will still get the signal, number 1. Number 2, even all the 3 channels are okay, I want to take out one channel for maintenance. So, it will operate on 2 out of 3 success criteria. So, this is called 2 out of 3 voting logic. So, that means what it means, unless and until if it can tolerate one failure, but if the channel out of the 2 out of 3, then the system has failed. 2 channel failure out of 3, system has failed. It will have further illustration, or will explain through some certain diagrams. Now there are 3, let us consider there are 3 discrete states for the system. One is healthy state, that means all the 3 channels are monitoring the same parameter and successfully providing the information in the control room. So, it is called healthy state. Okay. Degraded state, system is operating with only 2 channels, that means our margin, safety margin has gone down, because 2 channel monitoring. Now the question will come is, if the 2 channel monitoring, which channel is correct, it will be difficult to figure out. So, this is one difficulty, but so that means system has gone to a degraded state. So, one channel is out for repair and maintenance. Advantage, out of 3 we can take one channel out for maintenance, but at the same time our margin has gone down, because one channel is out and we are depending on only 2 channels. Then third stage is failed state, 2 or 3 channel failure. So, the moment 2 channel fail or 3 channel fail out of 3, then system fails. So, we will be creating, why we are discussing it, we will be creating, this is the first step in creating the Markov model. So, first we have to identify which are the states we are interested in developing it. Okay. So, first let us understand the background of this particular problem. As I was discussing, there are 3 channels. This is our system, which we are monitoring, and there are 3 sensors. Okay. Sensor 1, sensor 2, sensor 3, and this signal output goes to processing channel A, processing channel B, processing channel 1, 2, 3. Instead of A, B, C, we will say 1, 2, 3. And there is a 2 out of 3 voting logic for its operation also. That means when 2 goes high, the actuation demand goes and it actuates a safety device, and system brings the plant to the safe shutdown state. That is what we have to understand. So, how redundancy techniques are used in the plant? If we require only one signal, but we have 3 sensors and 3 channels, and the 2 out of 3 logic is basically to actuate shutdown, or safety actions, So, this is our system for which we are going to create Markov model. Okay. Here we have to also understand one thing, that 1, 2, 3 is independent channels, okay, but always there is a common cause between these 3 channels. So, how we will model in our Markov model, that we will see. So, one thing is, advantage of this configuration is maintenance can be permitted, the plant keep operating if you do maintenance on this. So, maintenance does not bring down impact anything actually. So, from state 1 to state 2, transition takes place by failure of one of the channel. Okay. So, in Markov model, any one channel failure or any channel failure will reduce it to the 2 operating state. So, that will be taking this particular thing from 1 to a compromise state. State 2 and all, this we are talking, and there is a common cause element which brings the common cause failure, which brings system to directly to failed state. So, there are 2 failed state to the root, one independent failures or common cause failure. Okay. So, before we go to the Markov model, real system, let us understand what is Markov model. Markov model fundamental tenets are the state, we have been talking left and right about it. The states are denoted by one circle. So, state 1 and state 2, That means systems state 1. So, we can say state 1 is operating state, state 2 is a failed state. And from state 1 to state 2, how will go? By this transitional arrows, So, these called transitional elements in the Markov model, arrows. So, by failure, lambda is failure and mu is repair rate and failure rate. So, from state 1 to state 2, it goes by failure rate, okay, or failure mode, and then from state 2 to state 1, it comes back by repair. So, normally the second last stage is called the absorbing state. But let us assume for this particular system, we are able to repair and bring back to the system to the operating state or healthy state, I would say. Okay. Then we have seen about transition diagram, their direction and their parameters, repair rate and failure rate we have over here, and so this could be absorbing state, but here we have considered that by repair we can make consideration of exponential model has been assumed. Actually, Markov model, when we have exponential distribution is generally inherent, and that is why we say the Markov model does not have a memory, because in exponential distribution the next state from t to t0 t to t plus delta t is determined by the future state, not by the previous state of the system. So, that is why it is said that exponential distribution is a memory-less distribution. It does not have take into account any past, or it takes only the future states. So, it is called memory-less system. Okay. So, now let us see, this was a simple diagram to discuss the various salient feature of Markov model. Now, you know the Markov model. Let us go to our problem again. So, Markov model for 2 out of 3 voting logic. Okay. 2 out of 3 voting logic. You saw what is that voting logic over there actually. So, P1 is the probability being in healthy state. So, here probability of being in this state is given by P1, probability of being in state 2 is given by P2, and probability of being in state 3 is given by P3. So, this is the initial configuration. Now, the question and then mu is repair rate and lambda is the failure rate. And again, as I was discussing, common cause effect also we want to analyze, lambda C, common cause failure. So, now you see how we go from one state to another state. Now, from state 1 to state 2, we go by 3 lambda route. Why 3 lambda route? Because channel 1 or channel 2 or channel 3, anyone can fail. So, that means there is a possibility of 1, 2 or 3. So, 3 lambda. Each channel has got its own lambda. Okay. So, 3 lambda will go to state. Now, it is a compromised or degraded state. That means, here 3 channels were operating, now it is only 2 channels are operating. So, that is why in maintenance, even if we take out 1 channel out of maintenance, we should revert back to the third mode, and maintenance gets only very short time for completing the maintenance on the channel which was taken out for maintenance. Okay. Now, mu can be repair time. So, so this is accounting for maintainability also, though it is availability diagram. Mu means repair time. If anything was found in the issue, it was repaired back. So, what we are telling here is we have only one repair station. So, limitation is not 3, but 1 channel we took out. So, logically we require 1 channel only, and 2 channel out is not permitted. So, mu as a parameter, considering only 1 repair station has been considered. Now, from 1 to 2 we saw from 2 it gets come back to 1 as a healthy state. Now, 2 are operating. Now, you see 2 lambda will take the state from 2 to state 3, that is failed state. We are calling P3 as a failed state. Now, but it is quite possible 3 channels were operating and common cause led to unsafe failure of that channel. So, lambda c, the cause, one single cause which impacted all the 3, it could be flooding, it could be humidity, it could be operator action, but all the 3 channels have failed. So, lambda c factor will come, and then also it is taken to the state 3, it is called failed state. It is interesting to draw the to write the differential equation for this, but it is easy also to understand. Now, I will explain you how. Probability of being in state 1. Now, you see the arrow which is going out and the arrow which is coming in. This is taking away from this state number 1 to state number 2. So, the quotient was 3 lambda. So, it was in P, probability of being in P, and 3 lambda root it is going out of this. Second thing is, by common cause root it was going to the state 3. Okay. So, P1 it was 3. Now, P2 by repair mode the system was coming back to the state 1. So, it was plus. It is interesting to note that it intuitive this differential equation, it meets the intuition, something is going out minus something is coming back to the state, is because we are writing equation for dp1 by dp2. Second equation is dp2 by dt, that means for state 2. So, 3 lambda will become plus here, lambda that is probability of being in state 3 lambda into delta p1. Okay. It is coming from p1 state. Now, mu p2. So, mu is become minus here because it is going out, this arrow is going out from this p2 state. So, p2 state and then to p2, yeah, this is also minus. So, the 2 arrows are going from here to p2 state. So, mu and mu root and 2 lambda root. Okay. Now, how p3 probably now for this you can write your own equation, dp3 by dt is equal to 2 lambda. 2 lambda is one root plus and another is common node. It is going to the absorbing state. Okay. So, this equation for state 1, 2 and 3, this was the core work that we have done. Now, this equation have to be solved. There are 3 parameters, 3 equation, it can be solved by simple arithmetic also, it can be solved by Laplace approach also. So, here we have done this job through Laplace modeling. So, you know that in Laplace transform we have to consider the condition at there is like probability of being in state is equal to 1 and at t is equal to infinity. That means, at time t is equal to 0, what is the probability of being in state is 1. At t is equal to infinity, p1t will be 0. Okay. And with this condition, we got this variation. Others are the s terms are coming in place of t, and we write the equation. So, 1 minus ps, probably on the last slide of this lecture, I have given all the formulation. So, by differential equation, how to write the Laplace term, those things are coming on over here. So, second state, and you can see this s is replaced because now we are in P2 position and P3 position. So, these are the 3 equation 4, 5 and 6, which is nothing but a Laplace transform of the original differential equation what we wrote on the previous slide. Now, let us say we try to solve this equation and we rearrange them so that it can get converted into a form where we can see these things. So, we saw earlier that these terms were there. So, simplest form it is come, this is my original number from Brook, they are appearing. Actually, this should be our previous numbers 7, 8, 9 and all that. That should be, yeah, 7, 8, 9, these are 7, 8, 9. So, that they will be 4, 5, 6 that equation 3.21, 3.22. So, this please take a note of this one. Okay. So, these are the 3 equations we have developed here for further solving. Now, what are the observations? Equation 7, 8, 9 are arithmetic equation with 3 variable. 3 equation, 3 variable. We can solve it overall. It can be solved to evaluate arriving at solution for Laplace transform. So Laplace transform require taking Laplace transform and inverse Laplace transform. Okay. The probability for state 1, 2, that is P1 plus P2 will give us the system availability, because P1 and P2 were system available state and P3 was failed state. So P3 will give us unavailability, system unavailability. So these are the observation, and with these observations we can solve this equation. And these are which are like for differential equation at time t is equal to 0, this will be 1, reliability 1, and this we have used Laplace transform of d by dt function of t, and this one equation, other places also. So this is a simple table which will be sufficing for reliability engineering for Laplace transform. If you require anything in the open domain, there are many more equations that are available, but I think this will be sufficient for exponential term. Laplace transform is a function is equal to f s minus a. So as and when it arises, you can use this. I have made it available to you. I would like to thank the researcher who has put this thing on the open internet, and I have simply brought it for you. Okay, as part of the dependability, the scope of this lecture covered availability modeling, definition of availability. We saw interpretation of availability and unavailability, how maintenance concept they come into the availability equation. Those things we have discussed, and the Markov model approach was introduced. Illustration of Markov model, 2 out of 3 redundancy technique, and your job, rather homework, is to solve this equation and formulate the final equation for system availability.